Hi everyone, my name is Yuan Zhang. I'm currently a PhD student at Rice University, the Department of Electrical and Computer Engineering, Efficient and Intelligent Computing Lab. Today I'm going to present one of our group's most recent work, GCOS, Gene Accelerated Core Search towards both better accuracy and efficiency. Firstly, we are going to briefly go over the general background and motivation for this work. As recently, graph neural networks have really demonstrated state-of-the-art performance on various graph-based learning tasks. For instance, node classification, graph classification, or recommendation systems. We conjecture most of the GN's amazing performance is attributed to their unique operations of aggregation and combination, or more specifically, as shown in this figure, by aggregating the neighboring features and afterwards using a dense connection to combine the features. GNs can better capture the relationship among the neighboring nodes, and thus better learn how to update the node features in the graph. As an example, the node A in this figure. However, these operations needed to be repeated for every single node in the graph usually, and thus pose serious challenges for the hardware acceleration. And in many cases, the GN's inference cost can be very huge. For instance, a two-layer GN on Reddit graph has 19 billions of floating operations, and it requires 5,000 times of latency to inference as compared to a 50-layer ResNet on a Xeon CPU. And we conjecture there are three major reasons for the huge cost. The first one is the prohibitively large number of nodes and complex connections. For instance, Reddit graph has more than 200,000 nodes, and each one with 50 neighbors per. And the second challenge we conjecture is the unbalanced and irregular connections among the nodes. Namely, some of the nodes in the graph have a lot of connections, while some the others only have a few connections. This level of dynamic workload poses challenges to hardware efficiency, as you need some non-negligible controlling overhead to consider these. The third challenge is the high dimension of the GN's node feature vectors, which directly contribute to the number of operations in the graph. For instance, CDCL have more than 3,500 features for each node. And to alleviate the issues above, there are two major thrusts of existing approaches. The first one is to develop the specialized GN accelerators, which use different level of customization to harvest the various efficiency. For instance, HYGCN and AWBGCN and balance workload across spaces and data areas, thus to increase the hardware utilization. GRIP and ENGN try to reduce the bandwidth consumption of the GN applications, so the computing unit idle time due to the communication bottlenecking can be reduced. Works like deep learning GL instead try to construct automated design tools for GN accelerator design to make it more flexible and accessible to more developers. And in terms of algorithm side, multiple lines of GN compression works have also been proposed to make the models more efficient and lightweight. For instance, GN pruning works like SGCN, robust GN aim to sparsify the connections in GN's graph adjacency matrices. GN quantization works like degree quant instead try to use a lower bit integer arithmetic for GN inference without sacrificing the accuracy. Works like GraphNet instead aim to find an efficient GN structure either through a automatic or insight-driven methods. However, either of these two major categories of solutions will have its own issues. For dedicated GN accelerators alone, they lack exploring the algorithmic opportunities. For instance, when trying to develop accelerators for GN models with absolutely no sparsity, that would be a dead end for efficient solutions, as no matter how well you design your hardware, the cumbersome algorithm will pull you back. For the algorithm side, without considering the hardware aspect, will very likely to make the result algorithm not necessarily hardware efficient. For instance, if the sparsity regions for GN models weights or features are extremely irregular in terms of the locations, then it will take a considerable amount of controlling overhead in order for the hardware to support this level of sparsity. Therefore, both of the two lines of work will result in suboptimal solutions if both task accuracy and hardware efficiency are our goals. Then the most sensible solution we conjecture is algorithm and hardware core design, and more specifically GN structure and accelerator architectural core search, which consider both the above algorithm and the hardware aspects during the design process and put it in an automatic search framework for better flexibility. However, naively combining the search for the optimal accelerators and the search for optimal networks will not simply work, as there are still three major issues for us to solve. The first one is the prohibitively large joint space, and at the same time, in contrast with the very sparsely designed, excelling both at accuracy and hardware efficiency. For instance, the combined algorithm and the hardware design space in our work can explode up to 10 to the 34th. And roughly only 4 out of like 9 times 10 to the 5th design choices barely satisfy the practical need in terms of the system throughput and also accuracy. The second challenge is the excessive retraining cost during the graph neural architecture search, i.e. GNAS phases. During the search for the optimal networks, each time a candidate network is sampled, in order to better evaluate the accuracy performance of the sample network, usually some retraining is needed. However, the retraining step will significantly slow down the search efficiency, posing serious issues when design space is huge, as in our cases. The third challenge is the lack of either generic hardware or gene structure search space. In order for the algorithm and hardware to mutually provide support for each other, a generic design space from either side is necessary. Otherwise, automated code search will not be feasible. Besides, a generic design space is also one of the major determining factor for the task accuracy and also hardware efficiency potential. And as generic designs in terms of the gene structure or hardware accelerator would reside from these design space. To this end, we propose GCOS, a GN and accelerator core search framework, aiming for both optimized accuracy and acceleration efficiency by considering the factors from both algorithm and also hardware side. And we are the first to jointly search for matched GN structures and accelerators. GCOS is composed of two major enablers to solve the three issues above, as we mentioned. The first enabler is a one-shot GN structure and accelerator core search algorithm, which can simultaneously and efficiently search for both networks and also accelerators. The second enabler is the generic GN structure and hardware accelerator core search space, with great potential in boosting the accuracy and also hardware efficiency. Last but not least, we use extensive experiments to validate the GCOS's effectiveness. We're going to go over the implementation details in the following fashion. First, we will show the overview of the proposed GCOS framework, then some key methods of the two proposed enablers. Then we will show some snapshots of the experiments to demonstrate the effectiveness of the GCOS framework. Here we present the overview of the GCOS. The entire GCOS framework takes the input of the optimization matrix, like for instance, the weighted sum of task accuracy and hardware throughput, which is to be specified by the user to either favor the hardware optimization or the algorithm optimization or a more balanced one. The home framework does not assume any statistics of the optimizing objectives, so we are able to take the black box objectives. The resource constraint, for example, the max number of processing elements, the max size of each storage components is a second input for the framework. The last input is the specified dataset, for instance, the correlation dataset on the node classification task. The framework then passes the inputs to the core parts of the GCOS framework, which is composed of two major parts, design space preparation and the design space exploration. Inside of the design space preparation, the algorithm space and hardware space will be generated and also tailored. For each task, and the hardware space is tuned. For each task, the hardware space is tuned, and each generated algorithm space through analyzing the sparsity patterns of the algorithm space. The hardware space can also be further tuned by analyzing the sparsity patterns and the weights and in the pre-trained SuperNet, and allocate the resource accordingly for much better hardware utilization template. When both the network and accelerator design space are finalized, our framework will enter the design space exploration stage to find the candidate designs trying to maximize the objectives given. Afterwards, the candidate designs will be passed for a hardware validation process in the format of synthesis and also placement and routing to make sure that generic hardware is viable. Finally, the satisfied designs will be outputted in form of GN structure and accelerator pairs. As mentioned earlier, to core search, The core search process is hindered by the prohibitively large and the sparse join space, and the excessive retraining costs during the search, which are the two of the three major challenges of the core search framework, or the core search process, as we conjectured earlier. To effectively combat these, we propose a one-shot gene accelerator core search algorithm. The entire process is inspired by the one-shot neural architecture search method and contain two phases, which are the SuperNet training, pre-training, and also choices exploration, as shown in this figure. For the SuperNet training, we adopted the uniform sampling strategy and a single path activation. Namely, each training iteration, we randomly sample a subnetwork from a SuperNet, which form our GN structure search space, and we will introduce it later. The sample network will only have one branch. This strategy will better decouple the weights among the subnetworks, and the backpropagation will be only conducted on this activity subnetwork. Besides, we also incorporate the weight sharing for the SuperNet training phases, i.e. the common blocks share the same sample network, share across the same sample network, will share the same piece of the weight. For instance, if two subnetworks sampled across two iterations, both have the same attention block type, then their weights in the attention blocks will be shared. This method has been shown to benefit the pre-training convergence. And both of the above two major points are for better estimating the subnetwork's fully trained accuracy during the search. Thus, the search process can be better guided to find the gene structure maximizing the task accuracy. In the second part of the core search algorithm, we employed the tailored evolution algorithm to efficiently explore the joint network and accelerator design space. Evolution algorithm through means of perturbing around the good designs and filtering out the bad designs. The sampling efficiency can be improved. As SuperNet is already trained, during the search, only inference is needed for the algorithm to get the estimate of the sample network's sample gene structure's task accuracy, thus eliminating the bottleneck from cumbersome retraining. Inside of the evolution algorithm, the network and accelerator description are combined into a single encoding, i.e. genomes in the terminology of the evolution algorithm. This is to enable the simultaneous search for both the accelerators and gene structures in one shot. The above then summarize our proposed one-shot gene accelerator core search algorithm. Next, we will present the core search space to effectively tackle the lack of either generic accelerator or gene structure space. First, we will focus on the generic algorithm space. As we presented earlier, we employ the one-shot NAS methods, and our network space is a tailored GN SuperNet containing numerous subnetworks pre-trained during the pre-training stage. The SuperNet can comprehensively cover most of the commonly used gene structures. For instance, as the table shows, to cover the networks with attention blocks, it will have attention blocks as part of the SuperNet and offer multiple attention types for picking. The candidate networks are sampled from these choices by choosing an option for each parameter. The entire space size can then go up to 10 to the 19th network choices, which gives us much versatile support for various applications and a large potential in achieving high accuracy. Next, we will present the proposed generic accelerator design space that is specialized for GNs in order to well support all possible design choices for the GN structure design space as we presented earlier. The accelerator design space is rooted from a proposed GN accelerator template. The searchable parameter will be extracted and is shown later. For a much more latency and utilization friendly design, the overall hardware template is composed of multiple individually customizable sub-accelerators. Each sub-accelerator will work on different parts of the features or weights, which are termed as different workloads. The hardware resource allocated to each sub-accelerator is proportional to the workload sizes each sub-accelerator got assigned, taking into account the sparsity of the SuperNet and analyzed right after the pre-training stage. Each sub-accelerator is equipped with functional units like dense sparse matrix, hybrid matrix multiplication engine, or the sampling unit to generically support different network structures. Besides, as different GN structures may have different preference on the data reuse patterns, trade-off among the available parallelisms, memory consumption, and bandwidth. Each sub-accelerator also has different tiling and scheduling configurations to cover different primary reuse strategies, i.e. input, weight, output reuse, and a different trade-off among parallelisms, memories, and also bandwidth consumptions. When the preference of networks in the design space can be comprehensively catered, the idle time of the hardware computing units are most likely to be significantly reduced, thus leading to a much improved hardware utilizations. The GN accelerator design parameters are then extracted from the template as shown below. Similar to the GN's structure design space, the candidate accelerator are assembled by picking a option for each parameter. The entire accelerator design space is composed of 10 to the 10th to 10 to the 15th design choices, leading to a combined core design space up to 10 to the 34th design choice, considering the GN structure design space as introduced earlier. Then to this point, we summarize all the key components of the GCOS framework, which are the efficient one-shot core search algorithm and the generic core search design space for both GN structures and accelerator architectures. Next, we'll present some experiment results to validate the effectiveness and also advantages of the proposed GCOS framework. We will evaluate our proposed GCOS framework on 4 datasets spanning across from the small-scaled ones like Cora datasets to large-scaled ones like Redigraph. To compare with other efficient GN structures, we choose both from the graph neural architecture search, GNAS generated, and also the manual designed structures. For hardware baselines, we validate the effectiveness of the GCOS's generated hardware from the by comparing with 3 example works, i.e. HYGSYN, AWBGSYN, and Deep Learning GL. We picked the Xilinx VCU128 as our hardware benchmarking platforms. When comparing with both SOTA GNAS works and manual designed GNs, as shown, the proposed GCOS consistently lead to a better performance frontier in terms of accuracy versus latency, as shown in this figure. The trade-off between accuracy and also hardware efficiency can also be much more efficient, as suggested by the much steeper trend in the figure above. Please note that for fair comparison, for all the algorithm baselines, as the paired hardware designs are missing in the original work, we'll use our framework to pick the best found hardware design for them and give the hardware efficiency in terms of latency. Next, we demonstrate the effectiveness of the GCOS accelerator parameter search capability alone. So as compared to the SOTA GN accelerators, when the networks are fixed for both GCOS and their baselines, GCOS is able to consistently achieve similar or even better speed up against the performance on the Xeon CPUs. The advantage is more obvious when the graphs gets larger, as in these cases, the tiling and scheduling is necessary and more important, as you cannot fit every single piece of data in the board. And the strategies of conducting the tilings and the schedulings is then matters much more. So GCOS versatile templates by offering different tiling configurations, that's more likely to yield a better fit hardware in terms of the reusing strategies or trade-off among different hardware components. That's in summary. We propose a GCOS, which is the first core search framework for both GNs and their accelerators, and to maximize both the task accuracy and hardware efficiency. GCOS is enabled by two major enablers: efficient one-shot core search algorithm and a generic core search design space. And we have shown the evaluation results to shows up to 35.98 times increase in the throughput, hardware throughput, and up to 3.22 increase in the percent increase in the accuracy. And finally, we acknowledge this work was supported in part by the National Science Foundation under the grant CREA 2048 183. and a National Institute of Health under the award R01HL144683. Thank you. If you have any questions, please ask me. Yeah.